Hi, in this lecture I'm going to talk about what is principal component analysis. It's a very popular technique in statistical analysis as well as in machine learning analysis. This is used in many reasons, but the main reason why we use principal component analysis is to reduce the number of variables or to reduce the dimension of the data set that we're working with. Okay, so it's basically known as dimension reduction technique. Okay, dimension reduction. Okay, so we will see the theory behind or the intuition behind the principal component analysis. It involves a lot of mathematics, but we will try to keep it simple, and we will also try to understand the intuition behind it. It's easy to understand the intuition, and the maths, of course, will come naturally when we are clear with intuition, and then we will take an example to understand what is principal component analysis, in short known as PCA, and how is it used for data reduction. Okay, as I've said, it's used for data reduction. Okay, so it is used to summarize data with, let's say, many variables. We have p number of variables with a smaller set of variables, and let's say we call that as k. Okay, so p is a large number, and we reduce the dimension to k. Sorry, so k is less than p. Okay, so k is less than p. Okay, so that's what principal component analysis is used for, to reduce the number of variables in our data. Okay, so that's as simple as that. All right, so here is a pictorial representation of dimension reduction. We have dataset A, which has got n observation and p number of variables. When we apply principal component analysis to this dataset, we have the same number of observations n, but the number of variables has now reduced from p to k. Now you see p is much larger compared to k, which is much smaller, right? So the reason why we use PCA is to reduce the number of variables and number of factors in our data set. Why is that so important? Because in many analysis we cannot such handle this large dimension of data. We cannot handle large number of variables, and not all variables are very useful. That's the second reason. And the third reason is that many times there's a repetition among the variables, in the sense that variables are very correlated. In those situations, in these three situations, we need to reduce the dimension of the data, so as to ensure that we build a model, a machine learning model or a statistical model that will be able to predict more or less, uh, to the extent that the original set of variables were able to predict. Okay, so the prediction ability should not come down, but we are able to bring down the dimension. Okay, and is the essence behind using principal component analysis. So it does a balancing act. So there is a clarity of representation and ease of understanding. So clarity and ease, these are the two most important words here. That the way we reduce the variables is not very complex, rather it is quite simple. Okay, and we will see how we can reduce this number of variables. It just is some rotation of axis, and then and so on. We will see that. Okay, and it's easy to understand why that rotation thing or reduction of variables does work. It doesn't reduce the information inside the data. Okay, because the fear is that when you reduce the number of variables, you might wonder that this will result in reduce in information, right? Okay, reduce in information that you have, but that's not the case. Okay, so the idea here is that we will reduce the dimension without reducing the information. Okay, or maybe to minimize the reduction in information. Okay, so we won't be able to harness or use the entire information, but we will use most of the original information that's there in the dataset. Second one is the oversimplification. uh, Sometimes we have we lose some information that is quite important. So that's a trade-off. Okay, so you need to decide as a model developer or as an analyst who is using PCA, you need to do this analysis or the trade-off between making sure that you're making your model simpler by reducing the dimension, but at the same time you are losing some information. Whether that some information is important for your analysis or not, something that there's no thumb rule as such, but you need to decide on your own. And you can do that. You can just do the cross validation. You can see whether the model is performing well in both cases. If that's the case, then reducing the dimension is the ideal way. Otherwise, if there is substantial difference in the prediction, then obviously we are losing so much of information. It's better to use the original set of variables. Sometimes computation also, computational complexity or power or limitation of computation, computational resources is also one reason why people use PCA. Although nowadays it's not an issue because machines or computers, servers that's available with us are very powerful. So computation is no more a big issue nowadays, but it used to be one of the reasons why PCA was, one of the many reasons why PCA was invented. It's probably one of the most widely used and well-known multivariate method. So let's go back to history. When was it invented and who invented this method? So it was invented by Pearson and Hotelling. Okay, they are very famous statisticians, and they first applied this technique to ecology, the field of ecology. It used to be called factor analysis, although factor analysis is very different from PCA, although the way we use factor analysis and principal component analysis in statistical modeling is similar, but the underlying theory is quite different. Okay, but the principal factor analysis is somewhat similar to the principal component analysis. So that's the history of. So it's been invented. It's 5 decades. It's been invented, right? Over 6 decades, in fact. So it does. The following. It's very simple. Okay, it takes the data matrix. You have n data points and p number of variables. Okay, n is the data points, p is the number of variables, which may be correlated. Okay, and many times your real world data would be correlated among themselves, and then it summarizes it by uncorrelated axes, which are just the linear combination of the original p number variables. Okay, so we can simply understand it very easily. Let's say we have x1, x2 and x3. These are 3 original variables. So there are p is 3 in our case. Now the principal component analysis algorithm, PCA algorithm, what it does is that it takes these 3 variables, input variables, and in the output it will give a lesser number of principal component. Okay, let's assume that we have only 2 principal component, p1 and p2. Now the idea is that most of the information that's there in x1, x2 and x3 will be there in p1 and p2. So the loss of information will be less, but the data is now transformed. It's no more the original data. You cannot explain the data p1, p2 in terms of x1, x2 and x3 directly. You have to take some transformation function to understand that, and that transformation function is given by the PCA algorithm. Okay, so which is just a linear combination of p variables. So basically your principal component p1 is some linear combination, let's say alpha 1 x1 plus alpha 2 x2 plus alpha 3 x3. Okay, similarly principal component 2 could be a linear combination of beta 1 x1 plus beta 2 x2 plus beta 3 x3. Okay, so this transformation is done by the PCA algorithm. A few more things to know in this case. Well, the way it does the transformation is that in such a way that both principal component 1 and 2 are orthogonal. So what do you mean by orthogonal? That means they are not correlated. Okay, they are perpendicular to each other. There is no correlation between principal component 1 and principal component 2. But x1, x2 and x3 are likely to be highly correlated. Although that's not the main motivation to going for principal component, but that's one of the motivation. The other motivation is to reduce the number of variables. Okay, so now we have come down to 2 variables out of 3. Okay, and we have also come down to 2 variables that are not correlated at all. Sometimes in statistical analysis, that's a requirement that your variables need not be correlated. In such situations also, although you are happy with the dimension, you still could think of using principal component analysis just to make sure the variables are orthogonal or uncorrelated. Okay. All right. So let's understand the rationale behind the PCA, or the intuition behind it. Okay. So for that, we will need to understand some of the basic concept of variance and covariance. So we'll need to understand few jargons. One is variance, the other one is covariance, and then eigenvalue, eigenvector, and so on. If you are already familiar with these things, then understanding PCA is very easy. If you haven't understood what variance, covariance, eigenvalue, eigenvectors are, I highly recommend you to check some of the linear algebra material. Khan Academy is a very good resource to study bit of this linear algebra. Okay, so it's an excellent resource where you can find many good videos on eigenvalue, eigenvector, and how to get eigenvalue, eigenvector for a given matrix. So once you are familiar with that, understanding PCA is very easy. So variance is just is just some form of denoting, or it's just a matrix rather, to denote how far each observation is from its mean. So if x is the variable and xi denotes observations, then we can calculate variance as summation of xi minus xi bar whole square. Okay, so variance is represented in square form. You take the square root, you will get the standard deviation. So that's variance. It's just the variation in the data. Okay, so how far each observation is from the mean. Okay, that's right. Covariance. Variance is again done with the same variable. So you cannot have variance of two variables. You can have variance of only one variable. If x is the variable, you can have its variance. But covariance is just including another variable. Okay, so you get covariance. So it's a co-movement, rather variation. Okay, so here variance stands for variation, covariance stands for covariation. Okay, jointly how they are varying. Okay, so two variables how they are varying. Okay, so when we take two variables, we call that as covariance, and the formula is slightly changed. Previously it was just square, right? Now we have just taken the first variable and the second variable, xim and xjm. Okay, so how xim is different from xi bar, so how first variable is how far it is from its mean, and how far the second variable is from the mean. You just multiply them, take the summation, and you will get the covariance. Okay, now all these two concepts are going to be used in calculation of PCA. All right, so the objective of PCA, principal component analysis, is to rotate, and I give emphasis on this because PCA algorithm simply rotates the matrix, and when we visualize it, we will be able to understand it better. The axis of the p-dimensional space to new positions. Okay, so it has got p-dimension, then from p-dimension it rotates the axis to a smaller dimension. Okay, and that's what is the main objective of PCA. And that has properties like it rotates in such a way that the principal component has the highest variance. That means the first principal component has the highest variance, and then it will be in the order, right? If there are, let's say, two principal component out of three variables. So principal component 1 will have the highest variance, and principal component 2 will have the second highest variance. So that will be in order. So why is that so? Because the idea is that a principal component 1 can explain the variation in the data. So variation is nothing but the, it's just a proxy for the information in the variables, okay, input variables. So if PCA1 can explain that, there is no need of PCA2. Okay, so you do that in order. Okay, the first one should essentially have the highest variance, and the second condition here is that they're uh, uncorrelated. So PCA1, PC2, PC3 are all uncorrelated. Okay, so that's what we have already discussed. Here is this example. So through visualization we can understand it better. Of course we'll go into a bit of mathematics behind it, but visualization makes much more sense if you want to understand purely from intuition point of view. So here is the data point, variable 1 and variable 2, and you see we have just plotted them on an xy plane, and the lines here that you can see are simply the means. Okay, so the mean of x2 is 4.91 and mean of x1 is 8.35, and we have just drawn lines parallel to the we just draw a line parallel to the axis. Okay, and these are nothing but the means, exactly where the mean is. Like it's 4.91, so here it is 4.91. We just create a straight line that passes through the data point. Here also we have drawn a line based on from where the mean is for x1. Okay, now this is interesting. Okay, why is it interesting? We'll see that in the next slide. The reason why it is interesting is that we want to know whether a single variable can explain the variation in the entire information. Just forget about the variables x1 and x2. Just take these data points for a while. Okay, now you can clearly see there are two trends in the data point. One is there is this particular trend, and there is this particular trend, right? But the actual variables x1 and x2, they don't quite represent this variation, right? The first variation, which is here, right? You can see if I just change the color of, you can yeah, so this one, right? So this variation is very prominent, you can see in the data, and the second variation is of course this variation. But the actual mean, the parallel lines that we just drawn, do not quite represent these two. And that's where it is interesting, because if you just rotate that, you will see the entire variation can be just represented. Okay, and maximum variation can be represented in the first axis itself, and that would, let's say, cover 70-80% of that. So that's the logic behind it, and of course it can be extended to higher dimension, not just one dimension. If I have 100 dimensions and you can brought it down to just 5 of them, imagine 100 variables have been brought down to 5 variables, that explains 80% of the variation. Isn't that cool? Because 80% of the variation have been explained by just 5 variables or 5 axes. So this rotation of axis is the main reason why PC algorithm is used. Okay, so I've got the variance and the covariance between x and y. One of the way we do it, and in fact it's important to do it, that before even we rotate the axis, we ensure that the data points are centered. The reason why we do it, because x1, x2 could be in different notations, not notations, different. I mean, they could have different units, right? They could have different units. If x1 is length, let's say, and x2 is, let's say it's height. If their length and height, they would be in different units, right? Length would be in centimeter or meter, and then weight would be in kg. So how do we rotate them? It's difficult. So firstly, we just standardize it. Standardize nothing but take the mean out of it and divide it by standard deviation. Even though if you do not divide it by standard deviation, you still call it a centered data, and that's what we have done here. Okay, So we have just, so there is a slight change you can see from the previous data. Is a slight change. This means the data is now, a little more center. Still, you can see the mean lines are, um, so obviously the mean line would now be different, right? I mean, these two lines are now slightly different. Even that doesn't represent, we still can rotate. All right, now you can see. As I was saying, that principal component algorithm, what it does is that instead of the original axis, it creates two artificial axes. Okay, so this is the y-axis in this case, and this is the x-axis, right? But if you represent this is x2 and this is x1, which is similar, right? XY plane, y and x, pretty much the same. It just rotates in some way. So now it is PCA2 and PCA1. You can see most of this variance you can see is now being explained by only PCA1, and the second most of the variance, okay, is now being explained by PCA2. Okay, if that would have been the case initially, then wouldn't have required the PCA transformation. But x1 and x2 were not that kind of, you know, the initial variables were not the representation of that thing. Now we have been able to do that just by transforming. How do we transform is of course a question that could be answered mathematically, but the intuition is that, right, you transform the axis in such a way that the variation is now captured by the principal component, which was not being able to captured in the original variables. Okay, so that's the idea behind this, doing this transformation of axis. Okay, because at the end of the day, what is important to us is that we should have a factor or an independent variable or an input variable that would have some variation in it, right? Variation is nothing but information. Okay, the information that we are seeking in an input variable is nothing but the variation in it. Okay, so that's one of the basic thing in statistics. And if we can catch hold of that variation, we get hold of that, we can use that in useful ways. And so now instead of using x1 and x2, we simply can use PCA1, because that itself is explaining a lot of the variation, could be 75%, 80%. So if you want to reduce that, instead of using both x1 and x2, you can simply use PCA1, and that would do a great job. Okay, so each principal axis is just a linear combination of the original two variables. So both PCA1 and PCA2 are simply the linear combination of the original variable x1 and x2. So you can represent PCA1 and PCA2 in terms of variable x1 and x2. Okay, and they are linear combination. There is no nonlinear form. This is linear transformation. So as I've already said, PCA can be just a1, y1, a1, y2. I mean, if y is the input variable, that's the way we can represent. Okay, in practice, of course, you will not have just two variables. Two variables is just a simplified version of thing, and of course, we can represent two variables in xy plane. But more than two variables, we cannot represent in xy plane. So it's very difficult to even understand. But that can be generalized across many variables or many dimensions. It could have p equal to 100. Okay, and if p equal to 100, we can just find out a couple of principal component that explains the variation in the entire 100 input variables. Okay, that's possible. The logic is just same. We just do the axis transformation in such a way that we we are able to explain the variation clearly. Okay, pretty much the way we did here, right? We just transform the axis slightly, right? This axis has been transformed like this, and this one also has been transformed like this. Some modification of transformation has been performed, so that now the variation is now within our reach to explain. So the algebra is something that can be generalized to p variables. It's not a difficult thing. Okay. Many times we wouldn't be able to use covariance, rather we'll have to use correlation. The example that I gave you, we used of course covariance, but if the variables are in different units, then covariance is an issue. Covariance is not immune to different units, whereas correlation is immune. Okay, correlation doesn't matter whether what unit in what unit you are expressing the variables in, but covariance is certainly an issue. All right, so if you use covariance to calculate the principal components, then what will happen is that the variables with highest variance, okay, will dominate the principal component. So what we do is that we just simply standardize the data. So we standardize the data and we take correlation. So these two are important. Okay. The reason why we do that, because unless if you don't standardize the variables, what will happen is that the variables with highest variance will dominate in the principal components. That's not what we want. We don't want a biased result, right? And the reason why we use correlation over covariance is because to make it unitless, right? Okay. Okay, covariance between standardized variables is correlation. Okay, so when you standardize variables and take the covariance, so you basically calculate correlation. Okay, of course you can calculate correlation without even standardizing it. But given the fact that we have to do both, we have to first standardize the variables, and then while calculating we need to calculate correlation. So that makes sense to first standardize before calculating the correlation. So after standardization, each variable has a variance of 1. Okay, and how you calculate the correlation coefficient? Well, the correlation rather, correlation between two variables can be calculated like this. You have the covariance and divided it by the the respective variance of the variables. Take this square root of that. That's the way. This is the formula to calculate the correlation. So take an example to understand how we can calculate the principal component. So simple example, x1 and x2 are the two variables and we will calculate. By the way, one thing I just forgot to tell you is that if you have p number of variables, you can have p number of principal component, maximum number of principal component. Okay. Of course, you will not need this p number of principal component, you will need less number of principal component, but you can have it. That's not an issue. Of course, you will take only k, which is k out of p. That means where k is much less than p. That's the main reason why we use principal component. But you can have the maximum number of principal component that we can have is p, okay, which is exactly same as the number of variables that we have. So the first step in calculating the principal component is just to first cross product matrix. Okay, so we take the standard deviation. We take the standardized variable. Standardized nothing but take the mean out divided by standard deviation. Okay, so how do we standardize x? So how do we standardize x? So x standard would be simply x minus x mean divided by the standard deviation of x. Okay, so this is some sort of a standardization. Okay. There are of course other ways to standardize, but this is one way of standardizing data. All right, so when you standardize for each and of course you calculate, you have this cross product matrix, you will have in the diagonals you will have the correlation between the two variables, and then you will have correlation between the same variables in the diagonals and between the different variables in the off diagonals, right? So correlation between two variables lies between 0 and 1, and it's not a negative number, by the way. Okay. 0 is no correlation, 1 is correlation. I'm sorry, it can be negative. Negative means it has a negative relationship. Okay, so it basically lies between -1 to +1. Sorry. All right. But the correlation with the same variable is just 1. So all diagonal values will be just 1 because the correlation with the same variable is always 1, is the highest correlation. So how we calculate the cross product matrix is just, if you represent it just take the transpose of x and then you just multiply with x, you get the cross product matrix of that. By the way, first you ensure that x is standardized. So just some brief about matrix multiplication. I'm sure you are aware of it. Just those of you who are not aware of it. So if x is a matrix, transpose is nothing but you just how do I say, you just change the column to row and row to column. You do that and you will get the transpose. Okay, and when you take the cross product of that, you will get the cross product matrix of these variables. Okay. And transfer, by the way, is denoted by xt, or some people denote it by x dash. Okay. And for transpose, you have, this is a 2 by 3 matrix. This is a 3 by 2 matrix. So these 3 should be equal to these 3. So basically, the number of columns in the first matrix should be same as the number of rows in the second matrix. These are some of the rules in linear algebra. I'm sure you must be knowing if you know linear algebra or matrix multiplication. The sum of the diagonals of a variance covariance matrix is known as trace. Okay, so it basically represents the total variance in the data. Okay, so this is a variance covariance matrix before standardization. So this is before standardization, and this is after standardization. Okay, so before standardization, the the variance between x1, of course, is 6.67, and for x2 it is 6.2. Obviously, after standardization, we only find the correlation, that is 1. It's always 1 for the same variable. So the trace here is 12.9 and the trace here is 2. Okay, it's the same. It's just that we are representing in two different forms. Here before standardization and this is after standardization. It doesn't make much of a difference to the final calculation though. Okay, so how do we then calculate the principal component? Well, finding out, and this is where the mathematics is, and of course this is slightly complicated, but if you keep an attention, I'm sure you'll be able to understand. We talked about the transformation of axis, right? We change the axis, we transform the axis in such a way that the information is that the original data is unchanged, but at the same time we have been able to capture the variation in the data in more accurate way. Okay, so principal component is nothing but a linear transformation of your original data. It's as simple as that. Okay, so we calculate the eigenvalues S from this characteristics equation, from this particular equation. So S are the eigenvalues, and sorry, S is not the eigenvalue. Sorry, S is the cross product matrix. I'm sorry, I just confused with the notation here. So S is the cross product matrix. Okay, here is the matrix, right? We just showed you. Okay, this is the matrix. So this is S. Okay, either of them, depending on whether you're taking before standardization or after standardization. We'll of course take after standardization. And lambda is the eigenvalues for, so lambda is again the vector, right? It has several lambdas, lambda 1, lambda 2, and so on, of S. Now this equation, if you solve, you will be able to find the lambda values, and lambda is the eigenvalues. Okay, so S minus lambda I is the identity matrix. Okay, identity matrix in this case in a 2-dimension is just 1 0 0 1, is a null matrix. Null matrix is nothing but 0 0 0 0. So if you solve this, so you know this is I, this is the null matrix, the right hand side. You know the S matrix in the last. You can easily solve for lambda, right? Easy, isn't it? If you are familiar with matrix algebra, it's very easy. So S we already know. S is, I guess, 1. Then what is that? Let me go back to see what is S. 0.5, 0.5297. Okay, perfect. 0.52, 0.521. So we know S, we know S, we know I, we know null, which is the right hand side. We just need to know the lambda. So we just said solving a linear equation, more or less exactly that. Once we have the lambdas, obviously we have been able to solve it, and we found that lambdas are 9.8 and 3.3. Now this is a transformation. Initially we had the trace to be 12, but now we have transformed the trace in such a way that lambda 1 is basically is now some form of a trace, which is first one is 9.8 and second one is 3.0. Okay, and if you add them up, you will find it's exactly same as the trace that we initially had. So if you add this diagonal matrix 6.67 plus 6.23 is equal to 12.9, and whereas the lambda 1 lambda 2 we found out in the previous equation, I have not solved it, but if you solve it you will get lambda equal to 9.87 and it's 3.03. If you just add them up, you will get the exact value. So what does it mean? That it means that now we have been able to transform the variation. Now remember, there is one we talked about how we are transforming to ensure that we are able to capture the variation in the best possible manner. Now you see, x1 is able to uh, contribute to the trace as 6.6. Similarly, x2. But now you can see lambda 1 is doing 9.8, lambda 2 is doing 3.9. Now the reason, or rather the pattern that we'll be interested here is to understand is that now lambda is contributing way more than lambda 2, whereas x1 is to contribute more or less the same as x2. Now here, if you do that, we can actually we can ignore lambda 2 and just simply go ahead with lambda 1. Just one variable will do the job. Okay, so the transform variable lambda 1, it will now do the job for us, because it is now able to capture a whole lot of the variation, which is nothing but a trace, right? And that's the logic behind PCA. Okay, and if you have so many variables, you will see that the top ones will have large values, and if you go down, you will have very small number of values. The lambdas will be very small. So that transformation happened in such a way. All right. Now you see the principal component 1 is able to explain 76% of the variation in the total variance. That's massive, right? Earlier, both x1 and x2 used to explain 50% of the variation, but now the first variable itself is able to explain 76%. So we don't need the second variable. Of course we need, because 24% is a good observation. But if you have so many number of variables, you can ignore the last few variables easily. Of course, we do not use principal component analysis for just two variables. It's just for illustration purpose, to understand how the transformation happens. Another example we'll take to understand how it's being used. And obviously in software it's all be done by the software itself. All you need to do is that you should be able to understand the result output from the software, and should be able to use that in the modeling exercises. So there are three in this particular example. We have 16 variables, and that's where we are important. We should be using PCA, by the way. Having two variables doesn't make the case very interesting, but when you have so many variables, we have 16 variables and we have 124 observations, and we will want to reduce the number of variables. Okay, we can use principal component analysis in this case. So we have used some software, and these are the eigenvalues we have found out. of course you can even calculate it, but for 16 variables calculating eigenvalues is very difficult task using hand. So if you are able to do it using a computer, that's much better, because there will be many equations here. 16 equations, solving 16 equation by hand is of course a very tedious task. So the first eigenvalue is 5.8, second one is 3, third one is 1.1, fourth one is 1.116. By the time you reach the fourth eigenvalue, you see 71% of the variation is now already being explained. You take to the fifth, it's 78%. By the time you reach the 10th variable, 94% of the variation is now already being explained. So the remaining 6% we can simply ignore. Okay, because the remaining 6% is explained by 6 variable, and 6 variable is a large number, but it doesn't contribute much to the information or the variation in the data. Okay, so we can simply ignore that. In fact, we can simply go ahead with 8 numbers, 6 numbers, depending on how much information you want. But there is no rule of thumb. The rule of thumb is that take the eigenvalues that's greater than 1. That's one of the main factors. Although you can of course take fifth, sixth, which are less than 1, but you should ideally go in for the top 4, because the eigenvalues are greater than 1, right? 1.16 here. All right. How do you interpret the correlation of each variable with the principal component? Remember, we said that principal component is just a linear combination of the original set of variables, right? So how do you explain the correlation, or because what you do is essentially is that you use principal components in a regression analysis. Okay, so instead of x1 and x2, you will be using PCA1 and PCA2 and so on. But they are transformed variables, by the way, and you can't explain them similarly the way you used to do with x1, x2. But it's only used for prediction minded. It doesn't help much in finding out inference for the original set of variables. It's only used for prediction. So you can interpret in a such a way that you will see the original set of variables are correlated with the principal components. Okay, so these are the coefficients. So these are nothing but the alphas. Okay, so if you take the linear combination of this correlation alphas with the original set of variables, you will be able to calculate PC using hand. You don't need a computer for that. You can easily calculate that. So if correlation values are given, so intuitively we mean that each element of the eigenvectors represents the contribution of a given variable to the component. Okay, so each eigenvector that you are getting, the lambdas, it represents how much a particular given variable is contributing the principal component. Here you can see altitude is contributing a lot, so it's an important variable. Okay. Similarly, you can see percentage of vegetarian is contributing a lot, it's 0.33. Okay, so it's also used many times to find out important variables in machine learning model building. You just calculate the PCA, take the correlation with the ordinary set of variables, see which one is having the highest correlation, and see that's also used. You can also look at the factor loadings on each of the axes while calculation of eigenvectors, and you can infer from there also. So question is now how many axes or how many principal components do we need? So the number of principal component we have, that many number of axes or new axes we are having, right? So the thumb rule is that eigenvalues has to be greater than 1, as I have said. So we just plot it, plot the number of, it's called scree plot, by the way. It's called scree plot, where we are plotting the eigenvalues with respect to the principal component axis numbers, and if it is greater than 1, okay, so here it is greater than 1, and just take anything above that. That's the thumb rule. Of course, you can take this. No harm in taking the lower ones, but that's what is the practice many people follow. Are there assumptions also in PCA? Yes, there are a few assumptions, not very strict assumptions though, but it's one assumption that if you're doing theoretical work in research, in academic research, these assumptions are more important. For industry, that's of less importance, because in industry we don't care much about the theoretical aspect. We rather are happy with if it does work for us in practice of a given problem. One assumption is that we assume relationship among the variables to be linear. Okay, there is no non-linearity here. Okay, which is of course not true many times, because variables are related non-linearly many times. And if the data is non-linear, that means the structure in the data is such that the variables are non-linear, then the principal component access that you will receive are not going to be efficient, or it won't be having the information summary of the data. Okay, so that won't work efficiently. So it is a matter of efficiency rather than um, you know um, you know um, a deficiency in terms of calculation. You of course can calculate and get your principal component without having an issue, but those are not going to be efficient enough for real world users. Thank you.